Today we're talking about how to create an exponential equation from a graph and a table. We've already covered this topic for linear equations, so we're going to change it up a little bit today and switch to exponentials. Knowing how to create an equation from a graph or a table is just as important as knowing how to solve the equation itself, especially when faced with real-world situations. So let's get down to business. First, let's review the general form for exponential equations. We have y equals a times b to the x power, where a, of course, is our initial value, b is the rate or multiplier, and today x and y are simply going to represent points on the graph itself. I know that our exponent always represents time and y is our total value, but when you're talking about the equation of a line itself, x and y are simply points on the graph. In basic exponential equations, if we know the y-intercept and the rate, we can write the equation. Now, by basic exponential equation, again, I'm talking about an exponential graph where no transformation has taken place. This is just straight basic exponential fun. So for instance, if I was given a y-intercept of 2 and a rate or multiplier of 5, I can simply plug them in, substitute them in for a and b into our general form, and I have the equation of my line. So if I'm given a graph, those are the two pieces of information that I need. I need a y-intercept and I need a rate or multiplier. So looking at this graph, right off we can say, oh, the y-intercept is at 3. And we already know what a is going to be in our equation. To find the rate, I need to look where the graph crosses the grid behind it. In other words, I want to look for all the places where I can tell what the coordinates of the points are. Not looking for fractions or decimals, because those will be very inaccurate. I can see that my y values of those points go from 3, then to 6, then to 12, and of course my next y value would be all the way off the graph up at 24. And just looking from 3 to 6, since these are exponential functions, we know we're multiplying as opposed to adding, we can say that we're multiplying by 2. Same thing goes from 6 to 12. We're multiplying by 2. And that's how I know my next points are going to be at 24, then at 48, and so on. So we say that our rate or multiplier of our y values is 2. And that's going to be b in our equation. So with our y-intercept being 3 and our rate of 2, we can go ahead and replace those in our equation. Just a quick note, one way to know that this is a simple exponential functions with no transformations that have taken place is to note that the asymptote or line where the exponential function is going to get really close but never actually touch or cross is that x-axis. And when your asymptote is on the x-axis, chances are you don't have a lot of transformation that's taken place. That's not always the case, but for today it will be. So then we can go ahead and write our exponential equation that represents this function, y equals 3 times 2 to the x power. Let's take a look at another graph. Of course, we can tell the y-intercept is at 8, and then I need to look at points where the line crosses the grid behind it. And we can see the y values of those points go from 16 to 8, from 8 to 4, from 4 to 2, from 2 to 1, and so on. Remember that in exponential functions, we multiply by our rate, we never divide. So from 16 to 8 and from 8 to 4 and so on, we have to find a rate that we can multiply by to get to the next value as I move from left to right. In this case, our rate is going to be 1/2. We're cutting those numbers in half as we move from left to right. So with a y-intercept of 8 for A and a rate of 1/2 for B, I can go ahead and write our equation. Y equals 8 times 1/2 to the x power. In our next graph, this looks a little different than the exponential graphs we've worked with before, because instead of curving up, this one curves down as you move from left to right. It doesn't change the equation that we use to write the equation of this function. We're still going to look for the y-intercept, which in this case is -2, and looking at points on the graph, we can see that the y values go from -2 to -6, and then from -6 down to -18. What value would you have to multiply -2 by to get to -6? And it should be the same value that you multiply -6 by to get down to -18. In this case, we're multiplying our y values by 3. Notice that our asymptote is still at y equals 0. It's still that x-axis, which gives us a good idea that not a lot of transformation has taken place here. That means that we can use our basic exponential function, replacing a with -2 and b with 3, and I get y equals -2 times 3 to the x power. Now on to tables. Just like with linear equations, we need to find the rate of change, or slope, and the y-intercept. You can see the y-intercept by finding the point where x is 0. The y-intercept is going to be at the point 0, 5, or I can just say the y-intercept is 5. Now to find the rate of change, remember these are exponential functions. They're going to be a little bit different than linear. Looking at the rate of change in our x column, we can see still we're adding 1 to get from one x value to the next. However, when we look at our y values, we need to look at what we're multiplying by as opposed to adding. An exponential function multiplies, a linear function adds. And we can see that going from 10 to 5, from 5 to 2.5, and so on, we're multiplying each y value by 1/2 to get to the next y value. To find our rate of change then, we're still looking for change in y over change in x. 1/2 over 1 gives us a rate of 1/2. That's not exactly what it does, but I'll show you in the next one how it can change. So now I have a and b. I can write my equation, y equals 5 times 1/2 to the x power. This next table will show us how exponential functions differ a little more than what we originally thought. We're finding our y-intercept, in this case it's at 9. Looking at our rate of change for our x values, notice that this time we're adding 2 to get from one x value to the next as we progress along our table. Looking at our y values, remember we need to look at what we multiply by, not add. And we can see that we're multiplying by 9 to get from one y value to the next. Now, I can't say that I put 9 over 2, change in y over change in x, to find my slope this time. As a matter of fact, if I'm multiplying by 9 to advance 2 x values, that means that I need to find what my rate of change is when I'm only advancing one x value. So to go from 0 to 2, I'm multiplying by 9, but I need to split that into two equal multiplications. With multiplication, you can't divide by 2. To split one multiplication into its two factors, I actually have to square root. To split this 9 into two equal multiplications would give me 3. 3 times 3 equals 9. That means every time I advance one x value, I'm multiplying by 3, and that's the rate I would use. If my rate of change on my x values were 3, I would find the cube root. If my rate of change on x was 4, I would find the fourth root, and so on. So don't forget, anytime your rate of change on in your x column is anything other than 1, you have to find the appropriate root to find your rate of change. And now that I have y-intercept and our multiplier, I can write the equation y equals 9 times 3 to the x power. Okay, I think that's enough for today. I hope the rest of your day goes great, and of course, I'll see you next time.